So here I have several different objects. Now if we look at the first object that I have here, which is a block, well, let's take a step back. Again, all of these objects have gravitational potential energy at the top of the ramp. We'll assume that they're all the same mass just for simplification purposes. But we know that this thing is not going to rotate. All right, so all of its gravitational potential is getting turned into translational kinetic energy. That means that this block is going to win by a landslide. But let's just take a look at these two objects here. So we have a solid cylinder and we have a hoop. Well, who's going to win between those two? Who's going to get second place? Because we know that this block is going to be the landslide winner. Well, what this comes down to is which one has less rotational kinetic energy at the bottom. Okay, so whichever one has less rotational kinetic energy and therefore more translational kinetic energy, that's going to be the winner. So what we can do is we can model these two mathematically. So I'm going to set up, we'll start out with the hoop here. I'm going to set up a conservation of energy equation. So I'm going to say mgh at the top is going to equal 1/2 mv squared. Okay, that's our equation for translational kinetic energy, plus 1/2 I omega squared. Now, here what we can do is we can plug in some different things in our rotational kinetic energy equation. Okay, notice how similar this equation is to our translational kinetic energy equation. Remember, we're just plugging in those rotational terms now. But what we can do is, I know that the moment of inertia of a hoop is mr squared. Okay, what this is telling us is that all of the mass is located at some radius from this axis of rotation, which is right at the center of this hoop. Okay, but I also know that my translational velocity is radius times omega. So what I'm going to do is I'm going to erase this stuff here. I'm going to plug in these new variables here. So what I'm going to do is I'm going to plug in my equation for moment of inertia, and I'm going to plug in omega in terms of translational velocity. Okay, so now what I'm going to do is I'm just going to simplify this thing way down. So if I square this term right here, well, that's going to leave me with, okay, I'm going to get rid of that. I'm going to end up having velocity squared. That's going to get rid of this r squared. My masses end up canceling out everywhere. So now from here, I can just do some simple algebra to simplify this down. So what I'm going to end up with here is GH is equal to, let's see here, V squared. So that then gives me a translational velocity for the hoop of square root of the acceleration due to gravity times the height. All right, so that's how fast that hoop is moving at the bottom of the ramp here. Now, I'm going to do the same thing for our cylinder. All right, so my moment of inertia of the cylinder, and again, you can look this up yourself, but it is 1/2 mr squared. So notice that we have a little bit of a different distribution of our mass. We have more mass located around the center of our axis of rotation here. So what does that mean? Well, let's check it out. Let's check it out. What does that mean in terms of the translational velocity? So I'm going to write out that conservation of energy equation again. So 1/2 times 1/2 mr squared. Oh, there we go. All right, now I'm going to simplify this algebraically again. So my r squareds are going to cancel out. Again, my masses are going to cancel out on both sides. So that's going to leave me with GH is equal to 3/4 V squared. So I end up then with the translational velocity of that cylinder to be the square root of 4/3 times GH. So what are we seeing here? Well, we're seeing that cylinder is going to be reaching the bottom first because it has a greater translational velocity at the bottom of the ramp here. Now, why is that? Well, again, the cylinder here has more mass located around the center or the axis of rotation compared to the hoop. The hoop's mass is all along that radius. Okay, so what does this mean for rotational kinetic energy and in terms of rotational inertia? Well, the higher the rotational inertia of that object, the more rotational kinetic energy you're going to have. Therefore, the less translational kinetic energy you're going to have at the bottom of this ramp. Now, we could model this for a solid sphere and a hollow sphere as well. And what we're going to end up seeing is that this solid sphere has more mass located around its axis of rotation. So it's going to beat this hollow sphere down the ramp. Once again, because it has a lower rotational inertia. So really what this comes down to when you're looking at rotational inertia, it comes down to this fraction right here. Okay, it comes down to this ratio. And we're going to understand rotational inertia a little bit more and how we actually get these equations in the next video lecture, which we're actually going to use some integration to solve for some of these. But all this is it's just giving us a distribution of where that mass actually is in terms of an axis of rotation. All right, so again, the soup can race was a silly means to an end, I guess you could say, giving us a very extreme example of how mass can be distributed to then affect its translational and rotational kinetic energy to then win that race. But the main key here is understanding that the higher a moment of inertia is, the more rotational kinetic energy you're going to have. And that, therefore, it's going to have less translational kinetic energy. And it's all dependent on the rotational inertia. And again, we're going to understand more how rotational inertia is actually derived for various objects that may be uniformly distributed, but we're also going to look at ones that have, kind of a goofy distribution of mass, and we're going to be able to solve for the rotational inertia of kind of those funky objects. So I hope this video helped in debriefing and kind of giving you an overview of what rotational kinetic energy and rotational inertia is all about. And then I hope the next video lecture also helps us more fully understand rotational inertia. Take care, AP Physics students.